Hey, hi everyone. Thanks for coming to my talk. This is going to be a little bit of a change in pace because today we'll be focusing more on core machine learning and some of the work that my group has been doing on one specific aspect of the application of machine learning algorithms in society, which is responsible machine learning. I'm an information theorist in background, so there will be some theory in this talk about some of these problems. The results that you're going to see today were done by a wonderful group of students and postdocs and former students and postdocs at Harvard, Shahab and Hiwan, who are now faculty in McMaster UCSB, Hao, Sean, and Well, the three of them just defended, and Lucas, Carol, Juan Felipe, Winston, and Lucy, who are at Harvard College. And this is the agenda for today. I'm going to start with a bit of overview and motivation about what is responsible machine learning. And this is a field that, even though you might not be entirely focused on this application specifically, it's something that can certainly benefit from machine learning tools and ideas, and also mathematical ideas from physics and mathematical physics to understand some of the fundamental limits of these problems. Then I'll talk about two specific aspects of this problem. One is something called group fairness, and the other one is predictive multiplicity. And then if I have time, I'll wrap up with some ongoing research challenges. So just to start talking about responsible machine learning, as most of you are aware of, data-driven algorithms are increasingly used to support decision-making in applications that have individual level consequences. These are applications that can change someone's life, something like education, loan approval, criminal justice, and so on. And in these applications, there's growing calls to ensure that these algorithms are developed and deployed in a trustworthy and responsible manner. The one recent call for this is from actually the White House, who put forward an AI blueprint for an AI Bill of Rights, where they state that you should not face discrimination by algorithms, and systems should be used and designed in an equitable way. So this problem of designing algorithms that do not discriminate, that are fair and trustworthy, is a complicated problem. It's a multifaceted problem represented here by this polyhedron, itself generated by an AI. And it requires dialogue between many different fields, between law, ethicists, stakeholders in these problems, folks that are developing these applications, machine learning, computer science, engineering, and so on. And today I'm going to talk about a couple of these facets. So one is on group fairness, which is this idea that we want to develop algorithms whose performance are similar across different population groups. And the other one is predictive multiplicity. And I don't think I'll have time to talk about a third axis here, which is fair use of data, but you can ask about this ask me about this later. A lot of the results that you're going to see today came out in the past couple of years at NeurIPS and FACT. These are conferences on machine learning and responsible machine learning. So if you want to learn more about this, you can check out our recent publications. So I'm going to start with group fairness and define the problem. So assume you have the following setting. You have a data set. And from that data set, you're going to take a sample X, feed it to a classifier, for example, a neural network, and this neural network is going to produce some kind of output H of X. For example, it might predict the probability that it might give you a probability of this sample X be part of class 1 or class 0, or what's the probability that this person whose data is represented by X might default on a loan, and so on. So the goal of group fairness, the challenge that group fairness aims to solve, is that given a certain set of population groups, we want to ensure that classifier performance should not change significantly across them. And what I mean by classifier performance, I'm going to talk a little bit more about this, but usually what this means is accuracy or false positive rates or false negative rates across different groups. And what I mean by population groups, well, this is not always easy to define. But for example, if you look at the blueprint for an AI Bill of Rights by the White House, they define it as groups based on their race, color, ethnicity, and sex. These are attributes that are usually legally protected in the American legislation. So examples of group fairness violations are widespread. Like there's even Netflix documentaries written about this. Like if you've seen this excellent documentary coded bias by the work by Joy Boloami, there has been widespread documented cases of group unfairness in facial recognition algorithms, healthcare and education, and so on. And the way, just to give you a little bit more detail on how these violations and how group fairness is quantified and measured in practice, just going to introduce a little bit more notation. So again, here we have an input example X. We have the output of a classifier that it will be a function of this random variable, of this sample that you draw from your distribution, denoted by y hat. And we have I'm going to assume that we have a certain set of predefined groups, S, determined, for example, by race, sex, ethnicity, and so on. And given these, and given that your prediction is binary here, that you're predicting 0 or 1, you can build group fairness metrics in this setting in the following way. In the simplest case where you have two groups and you're doing binary classification, the way these metrics are built, and these are there's several of these metrics that have been proposed by the machine learning community, is that you would build a confusion matrix for the first population with your true positive, false positive rates, and so on. You would build a confusion matrix for the second population, and by comparing differences in these matrices, you would define group fairness metrics. For example, one notion of group fairness is statistical parity, where you want to ensure that the average outcome across both populations marked as 1 is similar. This is important, for example, in loan approval, where you want to ensure that the fraction of loans that you approve across two different groups is approximately the same. You could try to equalize false positive rates and true positive rates. This is a metric known as equalized odds, but you can already see this and realize that there are probably combinatorially many other metrics and trade-offs that you can define from this table, each of them with its own properties, and this will depend on the application that you have at hand. It's also important to mention, and this will be important for us later on, so you might want to pay attention to this, is that you can define similar metrics of disparities in performance of a classifier when you have probabilistic classification. So what that means is that the output of your classifier is not 0 or 1, but it's a probability distribution. For example, a probability distribution over 10 classes or 2 classes, and gives you the probability of this sample belonging to a given class. Think about it as a neural network with a softmax output layer, if that resonates with you. And in this case, you can define similar metrics based on the probability distribution over the output of your classifier. These are some of these metrics. I'm not going to go into details because I don't want to clutter the notation, but you can just think about this as soft versions or probabilistic versions of the metrics that I presented before. What will be important for us, though, is that when you cast the problem in this way, several of these score-based group fairness metrics can be written as linear constraints on a classifier. The reason why this will be important for us later, because later on, we're going to use these constraints as constraints to an optimization problem in order to navigate this Pareto frontier between fairness and accuracy. So keep that in mind, this yellow box, because we're going to revisit this later. Probabilistic group fairness metrics can be expressed as linear constraints on a classifier. So given that you can measure these disparities, there's been several fairness interventions that have been proposed in the machine learning community that try to ensure high accuracy while closing some performance gap. This is one example of such comparative comparison between many of these interventions. This was done by Sorrel Friedler's group at Haverford College. This overview is already slightly outdated. I'll give you a more recent overview in a little bit. But the way these fairness interventions that aim to ensure group fairness while preserving accuracy are compared are with figures like this. Usually you get a data set. On the x-axis, you have some kind of measure of performance disparity. In this case, it's like statistical parity. On the y-axis, you have accuracy of the model. And you train a machine learning model, apply some intervention that tries to close the gap. And each one of these will give you a point on this graph, right? And you can do this across different data sets. And you can already look at this figure and see like, well, it doesn't seem like there's one method that rules them all, right? And there's been a significant effort within the machine learning community over the past, I would say 5 or 6 years to develop fairness interventions that aim to navigate this parental frontier. Like a recent survey that was posted on arXiv listed 340 publications and over 400 such interventions. So most of these interventions can be divided into 3 categories. This is certainly not a comprehensive list. You can see that there's not 240 references on this slide. But usually the way you try to ensure these group fairness metrics is either through pre-processing So you change the data prior to training a model. You preprocess your data, try to change it or randomize certain features in order to reduce bias. In processing, these are methods where you can add a penalty to your model during training, or maybe you retrain a model several times in order to ensure a given group fairness notion. And post-processing, where you do the thing that you can do out of the box with scikit-learn. You go and you train a model, and then you post-process its outputs in order to ensure some notion of group fairness. And what I'm going to do next is that I'm going to describe one more intervention that we added to this list, one more dot in that Pareto curve, but it's a pretty good dot, and it's based on information theory. And I'm going to prove later on that it approaches the information theoretic optimal Pareto frontier. So when we set off to address this problem, we wanted to design another fairness intervention that satisfied three properties. First one is that it would scale to large data sets of a nation state scale. So data sets with millions of samples. It would work in classification tasks with multiple classes, so not just binary classification. We want to ensure equitable performance when you're classifying individuals or outcomes over different classes. And it would also work for multiple potentially intersectional groups, right? When you have a large number of population groups that may intersect, you want to ensure fairness in performance. And as I mentioned, there are many fairness interventions out there, but most of them have certain limitations. They are either benchmarked on fairly small data sets that now are being abandoned by the community. Data sets like the UCI adult data set that you might have used in a machine learning 101 class, or the COMPASS data set, which is a data set on criminal recidivism. Or they only consider binary classification, or they ensure fairness for binary groups, only two population groups. And we propose a new fairness intervention called FairProjection that overcomes these limitations. And I'm going to explain FairProjection next and how it works. And I just want to highlight that it can be used for any number of classes and protected groups, as long as you have sufficient samples. Sample complexity dependencies are in our paper. We benchmark it on a data set with 1 million samples. This is a data set from the Brazilian university entrance exam. I'm Brazilian, so it's a data set that's open and you can go and test it. And you can apply this to any classifier without the need of retraining. It's a post-processing technique. And it's based on an optimization very similar to an idea in information theory called information projection, which if you've studied large deviations theory, this appears, for example, in the characterization of the deviation exponent. It's a post-processing method, as I mentioned. It amounts to tilting model outputs. It can be implemented using an ADMM-based algorithm. I'll say a little bit more about this, and it runs on GPU, which is nice because you can parallelize it. So let me explain a little bit more about information projection, so to show how FairProjection works. So information projection is an optimization formulation that you find in information theory, and it boils down to the following. You have a probability distribution P, and you have a convex set of distributions here denoted by calligraphic C. This is a set of distributions that satisfy, for example, certain moment constraints. And the problem of information projection is, given that you have a set determined by linear moment constraints on your distribution, you want to find a distribution Q within this set that's the closest in KL divergence for your original distribution P. So you're projecting it on the set in the sense of minimizing the KL divergence between the new distribution and the old distribution P. So you can generalize this problem like if you're just looking at this problem purely as an optimization problem, the choice of KL divergence is arbitrary. You can reformulate this in terms of a broader class of divergences known as F divergences, total variation, for example, log loss, cross entropy. These are examples and instantiations of F divergences. This generalization was proposed by Cheeser in 1995. And we extend this further to this idea that we call model projection, where instead of projecting a fixed distribution, we project a conditional distribution, right? So instead of projecting a P of X, we project P of Y given X onto a set of conditional distributions that satisfy a certain number of linear moment constraints. And then you can formulate the problem in the same way, but now instead of projecting your point P of Y given X, you try to minimize the average change in your divergence, represented here by this conditional divergence here. So this is not a direct extension of information projection. If you're interested in digging deeper into this optimization formulation, there are some technicalities that you have to take care of. For example, X might be infinite dimensional. Even to prove that this has a solution or this solution is unique requires a little bit of effort, but you can check out our paper from a few years back on this topic. But the reason I'm talking about this is because when I think about a classifier, for example, when I think about a neural network with a softmax output, I think about it as a conditional distribution, right? But it's a conditional distribution because features come in X, and the output is a distribution over a set of classes. Yeah.
So as a practitioner, how worried should I be about the applicability of convex set of conditional distribution?
I'll get there. I'll answer this question in about 4 slides. So just bear with me on that. And if you're not satisfied with the answer, you can ask again. So but again, this is just purely abstract formulation now. It's just like math on slides. So, but again, when I think about a classifier, when I think about neural network, I think about it as a conditional distribution or as a channel. And in this case, the goal here is to project this conditional distribution, this channel, this black box that maps a sample into a probability distribution over classes onto this set of constraints. And the constraints that we're going to use are constraints given by that ensure certain group fairness criteria. Remember that yellow box that I mentioned earlier, that a lot of score-based group fairness metrics can be written as linear constraints on a classifier. This is where it comes into play, because several group fairness constraints, for example, equalized odds and statistical parity, can be written as linear constraints on a classifier's output, as long as we use this score-based or probabilistic formulation of these metrics. And what this allows us to do is to formulate this problem of ensuring group fairness as a model projection problem, where we want to find this new hypothetical classifier, this new mapping P of y given x, that satisfies our group fairness criteria while minimizing the changes in predictions of an original base classifier. So a priori, if you look at this optimization problem, this HOP is just also an abstract quantity. It doesn't seem like it would have a simple form in practice, but in fact it does. And it's not difficult to show that the projected classifier, the optimal solution for this optimization problem, is a post-processing of the outputs of the original classifier. So what this model projection formulation tells you that if you want to find a model that's group fair and minimizes the changes in your original outputs, what you do is that you post-process your original outputs by this multiplicative factor. And this multiplicative factor is found as a solution of a relatively low dimensional optimization problem, which depends on a set of parameters lambda. These are dual parameters that will depend on the number of fairness constraints that you have. And so this tilting function has a simple form and depends on the solution of a fairly low dimensional optimization problem, where the number of parameters is the number of fairness constraints that you have. So the interesting thing here is that if you buy this model projection formulation as a premise, as a general formulation for ensuring group fairness, what this theory tells you is that post-processing is actually the optimal thing to do. And that's really good, because that means that the effort of ensuring group fairness in a classifier doesn't depend on the model complexity. It could be a neural network or deep neural network or a simple logistic regression. All you have to do is to try to solve this optimization problem and then multiply the outputs by this multiplicative factor in order to tilt or correct its predictions. And the algorithm that we call FairProjection does exactly that. It's an algorithm for computing this optimal tilting. Yeah.
Maximize the distance to the microphone. So on the previous slide, in terms of the optimality, can you comment a little bit more? Because sometimes, you know, you would naturally think, okay, maybe more data is giving me fairness, etc. So why do you focus so much on that?
Yeah, so this is so let me rephrase what I said. So in an information theoretic regime where we have infinite data, if we were to know the probability distributions, this is the optimal form of the solution. When you have finite samples, you will have to estimate this from data, and there will be there is an error associated to this estimate. But in theory, like if we knew the underlying distributions, and you formulate the problem as this model projection problem, the optimal solution has this form. The challenge then is estimating it in practice. And you can do so with an algorithm that looks like this. I'm not going to go into the details of the algorithm, but I do want to mention is that this is a specific optimization problem that's really amenable to optimizers that do primal dual splitting. So the methods like ADMM that are inherently highly parallelizable. So given a data set, you can try to estimate this optimal tail gain using this algorithm that runs on GPU. And you can check out the GitHub repository with this paper and see the TensorFlow implementation of this code. So let's see how it works in practice. These are just a few benchmarks on binary classification. The reason we benchmark it here in binary classification is because we didn't really find that many fairness interventions. In fact, only one other competing method that works for non-binary classification, for multi-class classification problems. Here, these are examples on 4 data sets. This is the data set I mentioned earlier. This is an open source data set made available by the Brazilian government on the university entrance exam. It has over 1 million samples. And it's a very interesting benchmark to test these interventions at scale. Here we have 4 other data sets. The star here represents the baseline model. This is what you get if you train simply a random forest classifier in these prediction tasks. On the x-axis, you have a group fairness metric, mean equalized odds, and the y-axis is accuracy. Higher x means higher group fairness violation. And you can see across these data sets, if you just train a random forest out of the box, you have high performance, but also a big disparity in terms of your fairness metrics. And the dark red line here is is FairProjection. And you can see it successfully closes this gap at a very small accuracy cost. Like this is something we observe across the board. You would think that, well, maybe ensuring fairness, I'm adding a constraint to the problem, it will decrease accuracy, but in fact, that's not necessarily the case. Like you can often close this performance gap at a very low penalty in terms of accuracy. The most competitive approach to ours is the reductions approach. This was proposed by researchers at Microsoft a few years back. The reductions approach performs really, really well, but it requires retraining a model multiple times. So it is also really slow, especially on large data sets. And in our case, due to the parallelization of the algorithm, we can get all the way up to 100x gain on these million sample sized data sets. And we have more benchmarks in the paper. I'm going to skip these, but also showing that FairProjection performs pretty well. So interesting. So that's a problem of group fairness. There are hundreds of fairness interventions out there. We introduced yet another fairness intervention. But an actual question to ask here is, what is the best fairness accuracy frontier, right? Should we keep developing these fairness interventions, or are we at a point of diminishing returns? So as an information theorist, a question that's really interesting for me is asking, what is the converse bound, this Pareto frontier between fairness and accuracy? And is there a region here that is simply not achievable, right? That this will depend on the probability distribution of the underlying data, but no fairness intervention could cross this limit. And in order to prove this, we have a preprint recently, and we use the theorem from David Blackwell on data processing result that helps us delineate this upper bound. And I'm going to quickly explain it next. So again, here's the problem that we're looking at. We have a group attribute, we observe an outcome y, and we may or may not observe s, but a y during testing time is certainly not observed. And you have an input example x for which you're going to feed it to a classifier output in order to perform a prediction. So this data has the following Markov relationship, s, y, x to y hat. All this means is that your classifier generates an output based only on your features x, right? Otherwise, it's trivial. You could assume that s is a part of x. But at least in theory, if we knew these probability distributions exactly, right? If we knew exactly what is the joint distribution of the underlying data, s, y, and x, we could try to use this information to compute the Pareto optimal frontier, right? We could try to solve over all possible mappings from x to y hat. This is the infinite data regime, the information theoretic regime, and try to find what is the best trade-off between accuracy and a given constraint on a given fairness metric. So our goal is to characterize the set of achievable distributions, right? The set of solutions, or the set of mappings from X to Y hat that satisfy this Markov condition. And based on that, try to delineate this optimal Pareto frontier. And again, just as a thought experiment in this information theoretic regime where the data distribution is known. And again, this is just a cartoon. You can think about the set of all possible row stochastic matrices. These are low dimensional sets that map SY to Y hat as this blue circle here in the set. So this is all possible joint distributions between SY and Y hat. But because of the problem that I have, that because of this Markov structure that I'm predicting Y hat given X, I can't search over all this space. So for example, if you give me one machine learning model, one neural network, this will induce a mapping between X to Y hat. That's what this model is this conditional distribution. And it's going to be one point in the space. And you have this other orange set, which we're going to call the set of achievable conditional distributions. Those are the ones that, given the data generation process, that you observe X and you're predicting Y hat, this constrains the form of these matrices P of Y hat given SY that you can observe. So most fairness and accuracy metrics can be cast in terms of this fairly low dimensional object. You can think about Y hat and Y being binary, and S being the number of groups that you're trying to ensure fairness for. So if we could characterize this achievable set, we could find the best possible information theoretic fairness accuracy frontier, which is exactly this purple line that we could want to express. We could solve this optimization problem where we maximize accuracy subject to a fairness metric, given that our conditional mappings are within this feasible set. So the challenges in doing this even is, first, we do not know the distributions in practice, right? So we don't know what the distributions are. But even if we knew the distributions, the features X could be fairly high dimensional. So even casting this as an optimization problem that we can feasibly solve in a computer, it could be challenging. Think about Y being, is this person in this image smiling or not? So it's low dimensional, but X is an image, which is a very high dimensional quantity. So the key idea to create this frontier is to create a tractable outer bound for this set that's computationally tractable and solve this optimization problem over this computationally tractable outer bound. We're relaxing our constraints, and this will give us an upper bound on the Pareto frontier against which we can compare existing metrics. So one way of doing this is using data processing inequalities from information theory. So processing data does not increase information, right? If you've taken an information theory class, you've seen this before. And that gives us a constraint on the set of probability distributions that we can navigate here. But this constraint can be very loose. So what we do is that we use the ultimate form of the data processing inequality. This was proposed by Blackwell in the 50s, where this condition holds if and only if this channel P of X given SY is more informative than P of Y hat given S and Y. I'm running out a little bit out of time, and there's one more thing I want to talk about. So I'm just going to skip the theorem here. This is the theorem by Blackwell that gives exact conditions on this inequality to hold. And the key idea that we have is that we approximate these conditions on the set of probability distributions using a piecewise linear approximation of this outer set. And you can formulate this as an optimization problem that you can solve on your computer. It's a difference of convex optimization functions. It's not a convex problem, but what it does is that it approximates this set via a set of cuts of linear constraints that you can estimate given some knowledge of the underlying probability distribution. And we can form this as your outer approximation of a feasible set of distributions and use this to solve and characterize an upper bound on the Pareto frontier between fairness and accuracy metrics. And when you compare this in semi-synthetic experiments where you give me a data set and you assume that that data set is the ground truth, right? That's a semi-synthetic experiment, and we resample from that data set to compute this upper bound, we can compare FairProjection and the reductions approach against this ideal information theoretic optimal given by this red line here. It's what we call fair front. And we can see that we're really, really close to this Pareto frontier. What this means is that there's very little gap between the best that we can do and the achievable fairness interventions, the state-of-the-art achievable fairness interventions that have been published in the literature. So the takeaway here is that this problem of group fairness is really important. It's a problem that we find in practice. And we are close to this information theoretic optimal fairness accuracy frontier, at least in theory. There's diminishing returns in trying to generate yet another set of fairness interventions that ensure accuracy given these specific group fairness constraints. So to wrap up, I just want to quickly introduce another problem because as I mentioned, group fairness is only one aspect of fairness and responsible machine learning. There are many other aspects to this problem. And one of them is a term we coined predictive multiplicity. So let's go back just to the setting that we are looking at. And in order to understand predictive multiplicity, you have to understand the Rashomon effect. So consider the following problem. You have a data set X, for example, X-ray images, and you're training a machine learning model, let's say a neural network, to predict if that image contains pneumonia or not, if that X-ray of that lung is the X-ray of a lung with pneumonia or it is not. So when you fit your neural network, you're usually going to do this via backpropagation. And there's a ton of decisions that you have to make during this process, right? There's fairly arbitrary decisions that a data scientist will make when initializing training. You would set your random seed, you would initialize your weights, set a dropout rate, shuffle your batches. We're going to call this some random initialization. And every time you start your training process with a different random initialization, you're going to end up with a different model. These models, during testing time, they might have very similar performance. Basically, their loss might be statistically indistinguishable from each other. This phenomena, where you have multiple models that are different, have different parameters, but have statistically indistinguishable loss, is known as the Rashomon effect. This was introduced by Leo Breiman in the early 2000s. Rashomon is because it's based, the term Rashomon comes from the Akira Kurosawa movie from the 50s, Rashomon, where different people describe the same crime from different perspectives. And similarly, here you have different models that are different, but achieve similar average loss on a given learning task. This parameter epsilon is known as the Rashomon parameter. And this Rashomon parameter is always non-zero if you have a finite data set, right? If you have a finite samples, you cannot say what your loss is exactly, and you're always going to have some uncertainty associated with the estimate of that loss. So, and you can think about the Rashomon effect as partitioning your hypothesis space, your space of neural networks in these islands of models that perform reasonably well. We call this the Rashomon set, and that will depend on your Rashomon level parameter epsilon. So the Rashomon effect is the phenomena where you have multiple models with similar average performance, but they're different, right? They're different and have different weights. What predictive multiplicity is when you feed an individual sample, one sample, to these different models, they might produce conflicting predictions. Even though on average they have similar performance, but for that one sample, they might disagree. This is what we call predictive multiplicity. Competing models assign conflicting scores to individuals. And this problem is widespread and these over-parameterized, under-specified problems that you try to solve with neural networks. You can find it in image classification, in text classification, and in audio classification tasks. And in terms of responsible machine learning, predictive multiplicity is really important because if it's not accounted for, models supported by machine learning, decisions supported by machine learning models may depend on arbitrary and unjustified choices. So think, for example, certain applications of ML. One was recently announced by the Brazilian government that they're going to use AI to grade the university entry-wise exam. And you might deploy a model that on average performs really well, but if the person who developed that model could have chosen a different random seed, maybe the score for one individual student would have changed, right? And the same issue appears when you have algorithms that are shared or monopolize access to critical opportunities, like credit scoring, right? Maybe your credit score would change if just a different initialization were made when training the model, or maybe there exists a competing model with similar average performance, but on my specific data would have given me a different score. So how can you measure predictive multiplicity? We have a recent paper on this. I won't have time to talk about it today, but you can check it out. This was just published at NeurIPS last year. And I just want to show some data here just to show that this phenomena is widespread. You can ask your graduate students, or if you're a graduate student, you can do this experiment now. Get a model that you train on your physics data and just perturb the weights a little bit so that the loss doesn't change a lot. and see how the predictions change. And you're going to see that there was consistently sets of samples for which you observe, with a very small change in loss, even 1%, you're going to see a high variation on the predictions for a certain set of samples. So you can see our paper for many more numerical results on the topic. So we also identified predictive multiplicity and other problems. For example, if you care about privacy, differential privacy algorithms tend to exacerbate predictive multiplicity. The issue of, we have a recent preprint where we demonstrate that this problem of multiplicity is in fact orthogonal to group fairness. Ensuring group fairness does not necessarily decrease multiplicity. And in some circumstances, it can actually increase this variation in score or the size of the Rashomon set. We can talk about that more later. And these are the takeaways that I hope you take from this section of the talk. The first one is that even if you're developing models in physics, you should always measure and report predictive multiplicity. I guess in science, you would call that replicability, right? So your results might be reproducible because you made the code available online in GitHub, and everyone can go and run it and reproduce the same graphs. But maybe with a small change, just a random seed that you use to initialize the weights in your neural network, maybe you would end up with a model that on average is very similar, but for certain samples, predictions would be wildly different. And that's something that we observed in practice. In terms of responsible machine learning, decisions supported by machine learning models without regard for multiplicity may be arbitrary. For example, there might exist different models that would have made a different prediction for certain individuals. And there's a lot of needed research in this area. Like, we don't actually have efficient methods for characterizing the Rashomon set and reporting multiplicity on a per sample basis, particularly for very large overparameterized models like deep neural networks. So these are some of the facets of responsible machine learning. Another issue that I'm interested in is fair use. Ask me after the talk or during the break. As I mentioned, I'm an assistant professor at Harvard, so I'm always looking for collaborators, especially in this area. We have many other problems on that we've been working on: correspondence analysis at scale, fair use of group attributes. We also do a lot of work on privacy, and there's a very interesting connection between privacy and statistical and mathematical physics. If you want to understand what is the connection between Schrodinger operators and differential privacy, which is the standard of privacy that's used in industry today by Apple and Google, ask me also during the break. And there's other problems that we've been looking on how to compress very, very large data sets, but have many similar images and a lot of redundancy in it, and so on. So I'll stop here, and I'll be happy to take questions. Thank you.
Questions for our speaker?
Yeah, thanks for a very nice talk. So in terms of class, you talked a lot about classification. Can you say a few words about regression?
Yeah, that's a good question. Yeah, so the results that I talked today are very limited to classification and prediction over discrete classes. There are metrics for group fairness in regression. You can formulate it in terms of, for example, a squared error between different groups and so on. More interesting metrics have been proposed recently in terms of ensuring that classifiers are well calibrated and these errors are well calibrated across different population groups. This is a notion known as multi-calibration and multi-accuracy, but we didn't address it here. But there are methods for, there are quite a few fairness interventions focused on regression, but they're not included in what I talked about today.
Thanks for bringing up some really interesting ideas and challenges. So in this last part about predictive multiplicity, where you say that we're subject to arbitrariness, doesn't the existence of the Rashomon set mean that no matter what we do, something is an arbitrary choice?
Yeah, that's a good question. So I think there are two sides to this. One is the problem being underspecified and the solution set being non-unique, right? So the existence of a Rashomon set. So in a sense that could lead to arbitrariness. You might have a training algorithm that always arrives at the same point in that Rashomon set or a similar point. If the problem is strongly convex and well, in a sense, well specified, like the predictions that you have might not change that much. But yeah, the existence of a Rashomon set does imply some level of arbitrariness. What folks have been arguing in this and in the literature is that you can view the existence of the set both as a blessing and a curse. So the negative side is what I talked, predictive multiplicity, is when the choice of a model in the set is arbitrary. You cannot justify it, or maybe you're choosing one without realizing it just by setting a random seed. But it also presents an opportunity, because the fact that you have models that are similar on average either gives you the option to explore additional criteria for model performance, like interpretability. So there's a line of work by Cynthia Rudin at Duke, where she argues that, well, we can, for any good model, we can probably find an interpretable model with almost similar performance in this Rashomon set. Or you could potentially do some kind of combination of models or some kind of ensembling, and therefore even boost performance further.
I wanted to ask, I think a lot about data augmentation through active learning. So you have a small subset that you've trained a classifier, for example, on, you're thinking about how to increase that training data set in specific ways to make your model more robust. I was wondering if predictive multiplicity could be the basis for doing that kind of data augmentation, if you can identify by little tweaks and wiggles of the weights where your model is most uncertain, and use that to add to your training.
Yeah, I think you can. I think I haven't seen a lot of work on that, but I think that's a really interesting direction. There's a lot of work on robust and adversarial machine learning, where you tweak the input of the model and see how the output changes for a fixed model, and then you try to develop a model that's robust to such adversarial changes. The opposite, I haven't seen a lot of work on, where you try to tweak the weights of the model in order to identify samples for which it's not super confident on, or maybe ways of augmenting the training data and then retraining. That would be very interesting.
Other questions?
Thanks for the very interesting talk. In particle physics, we also are interested in training decorrelated classifiers, which I think is the particle physics version of fairness. And actually, I was interested to see in your examples, are the protected features always discrete?
Yeah, in the examples I gave, they're discrete. And
so because in our applications, we're generally interested in protected features that are continuous valued.
Yeah, so a line of work you could check out is what I mentioned on multi-accuracy and multi-calibration. This is fairly recent work where they have a more general approach for these protected sensitive attributes, where they assume that you have a family of functions, and these functions could be continuous potentially, and you want your error to be decorrelated from those functions. So it might be very much in line with what you're mentioning.
Yeah, it's very interesting. And also we generally have one metric we're interested in, I think is what you call statistical or demographic parity. But I'm curious, yeah, it's interesting. Maybe we can discuss offline what the other metrics would correspond to in our context. Yeah, thanks.
Maybe one final question. Yeah.
Yeah, I don't have so much as a question, but just to say that I feel like this is really important work, and it's nice to see it approached from a logical and mathematical perspective.
Yeah, thank you. I appreciate that.
All right, let's thank our speaker again.